This is one talk, not two talks. You should feel free to ask questions. This is a talk about a research program that I started about 11 years ago. So it's covering quite a bit of stuff, but it's a lot of fun stuff too. It's going to be partly drawing upon a tutorial that I gave at the last ICML. So you can go there to get references and things like that. It's going to be talking about VW and about the decision service, which are at these URLs. Oh, and of course, many, many people have helped me here. Many more than I could easily fit onto this page. Okay, so let's start with supervised learning. Supervised learning is what people are most familiar with. And in supervised learning, what happens is you have some, let's see, does this work? Oh, yes. Okay, so you have unlabeled examples. You get labels for them. You shove your labeled examples into your training algorithm. And then out comes a classifier that can then take an unlabeled input and give you a label as output. So that's simple supervised learning. And supervised learning has done amazing things. So in particular, speech recognition now works using supervised learning. And image recognition is now, people have moved on from the ImageNet data set because it's become too easy. So people are getting to the point where, well, computers are getting to the point, or people programming computers are getting to the point where they can now recognize objects and images routinely. So this is a great accomplishment. And now, okay, so what is, how can we think about supervised learning? We can say, in supervised learning, we regard a problem as solved if a human can tell you the right answer. Right? So you have the unlabeled data, you hire somebody to label things, and if somebody can label things correctly, then it's the job of the machine learning algorithm to figure out how to map from that unlabeled input to the label. Okay, so, and then I guess there's a caveat here, which is that you need to be able to tell the right answer many times. Right? So the data sets that are used for image recognition or whatever tend to be quite large. Okay, so this is what supervised learning is. And now people are trying to apply supervised learning all over the place. So let's think about doing personalized news. Right? So what happens is a person comes to a website. There's various news articles of the day which could be displayed to the person. And the computer makes some choice about which news article to suggest to the person to read. And then the person either reads it or does not read it. Okay, so there's various ways you could try to think of this as a supervised learning algorithm. You could try to hire editors to predict which article would be of greatest interest to each individual person. You can also try to treat a click as a label information. So you can say, look, I have collected historically some information about a user, the article that they saw, and whether or not they clicked on that article. And they can try to build some features of the user in the article, and they try to learn to predict the probability of the click given the features of the user in the article. And then they can try to act according to the argmax over the articles of the probability of the click given the features of the user in the article. This would be a standard approach. This is not quite supervised learning because you're sort of not hiring somebody to say whether or not what's the most interesting news article. Instead, you're trying to derive this from the actual event stream that you're observing. But after you finish this, maybe you deploy this into an A/B test for 2 weeks, and what happens? Right? So you deploy this into an A/B test, and it fails. I've seen this fail personally several times. This is actually it's not like a stupid failure. This is a fundamental failure of the approach. Okay, so now let's think about it. Why is this actually failing? So there's actually two different issues which can cause a failure, and they're both interrelated and doubling up to cause a failure here. One of them is it's very difficult to make the right prediction if you don't have the right information. So is Ukraine interesting to John? Do you know that? So it turns out my wife is from Ukraine, and so I would be interested in a news article about Ukraine. But unless you had previously displayed a news article about Ukraine, I wouldn't have known that. This is also showing why the editorial approach, where you hire somebody to label things, can be very difficult. Because there's no way that somebody could look at my browser cookie or my geographic location and figure out that I'd be interested in this. Right? So you need to get the right information, the right signal to get the right answer. And just looking at the historic log there's no guarantee that it has the right signal in it. Right? So the information may not be there. Maybe the policy which was gathering the data never actually displayed an article about Ukraine to John. Okay, so this is a fundamental issue. If you don't have the right information, you can't succeed. This is not a question about the quantity of information, this is a question about the right information. So in particular, this is not about overfitting or underfitting or anything like that you're used to from supervised learning. You can have an infinite amount of information, and if it's the wrong information, you won't succeed. Okay, so that's one issue. Another issue is essentially non-stationarity. So this is from real data. We built a personalized news recommendation system for MSN. And if we took our model from day one and we showed it on day 2, most of the value went away, or half the value went away. Oddly enough, it actually came back a little bit on day 3. But the point here is that the world is very non-stationary in this problem. And so you cannot wait 2 weeks to evaluate a policy. So when you put out an A/B test, you fix your policy for a period of 2 weeks. And that means you end up averaging this and this and this when you really want to be learning constantly from what's happening in order to maximize your performance. Okay, so news articles come in on an hourly basis, and they decay in value over a day level basis. So that non-stationarity is much more extreme than in many other machine learning problems. Okay, so are there any questions about this? Okay, so supervised learning is not going to work terribly well here. And the question is, how do you get beyond supervised learning? And of course, the claim is that a reinforcement approach is what you want. So there's a more fundamental thing than what is the right answer. There is, oh, that was good, or oh, that was bad. So we have many symbols for good and for bad. And now the question is, how do we learn from a reward signal? Okay, so that's something people have worried about for a long time. I'm far from the first person to think about it. So we can think about reinforcement learning as a process where you have an observation from the world, and then there's some policy which is going to make a decision. That policy chooses some action. That action acts in the world, and then you see some reward. Okay, so that's straightforward. And now the most common kind of reinforcement learning that you observe is multi-step reinforcement learning. If you go and look at the people at DeepMind, they've been solving Go. They're thinking about multi-step reinforcement learning. So there what happens is you have an observation, you have a policy choosing an action, and then you have a reward, and now you have another observation and a policy choosing an action, and then you have a reward, and it just keeps going over and over again until finally you get to the end. So you have some episode of some length, right? So maybe you finished playing the game of Go. And your goal is to maximize the sum of rewards. So this is basic multi-step reinforcement learning like you might learn about. And I'm going to show you something which, so the applications are all over the place. This is a very natural way to phrase a problem. And so just about every problem can be mapped into this sort of phrasing. But there is an issue with multi-step reinforcement learning. Okay, so let me apologize. We had to move my slides, so the font are slightly off. I worked on a bunch of papers in this area, but there's a caveat that I want you to think about for multi-step reinforcement learning. The caveat is that it's not really a solved area. And in particular, there are very simple problems which will break essentially all the commonly used multi-step reinforcement learning algorithms. So I'm going to tell you a problem of the flavor which will break the common multi-step reinforcement learning algorithms people use. Okay, so suppose you have a boy who's out camping. He's at a fire, and the fire starts to die down. So what the boy needs to learn to do is he needs to learn to go grab a log and put it on the fire, right? So naturally, you have some simple exploration algorithm, something like epsilon greedy. The boy starts exploring. He goes searching for wood, but as he steps away from the fire, he gets cold, right? And so the immediate reward pushes him back towards the fire, right? And so the boy goes back to the fire. He's warm for a while, and then the fire goes out, right? Okay, so this is the structure of this problem is one where the immediate reward structure is the opposite of the long-term reward structure, right? So if you try to optimize your immediate reward, you'll end up failing to optimize your long-term reward because you'll fail to get the log, and then you'll fail to keep the fire going. So this structure of a problem where the rewards, the immediate rewards and the long-term rewards are misaligned can break essentially all the common reinforcement learning algorithms, because what happens is you learn immediately a local policy which pushes you back towards the fire, and then in order to discover that you need to go here and get the log and bring it back, you need to overcome an exponential barrier. You have to do the epsilon case in epsilon greedy exploration t times to get to the log and bring it back. And that never happens because 1 over the epsilon to the t is like infinity, and then you never actually learn. Okay, so that's kind of disappointing. I think what happens in practice is many times you don't have the structure. Many times you spend a lot of effort figuring out how to shape your reward function so that this problem doesn't occur. Sometimes you just hit it with a really hard stick and just blast through a zillion examples until that one case where you grab the log and take it back to the fire occurs, and so your sample complexity is 100 million or something. This is what makes reinforcement learning actually quite difficult to apply in practice. And typically you need experts to figure out how to shape the rewards and when you can afford to just hit it with a sample complexity hammer using simulation or something like that. But it turns out there's a special case. The special case is if you just have an observation, a policy which chooses an action, and then you see a reward, and your goal is to maximize the immediate sum of rewards. So this is what I would call a contextual bandit. The history of that name is interesting, but you have context, which is your observation. Why is it called a bandit? It's because the problem started out in theory land, and it was called the bandit problem, as in you're going to Las Vegas and playing with one-armed bandits. So about 11 years ago, I started working on this problem, and we've been doing a lot of work on it since. And at this point, this is you can really use this in practice. This is a substantial step beyond supervised learning that we can routinely apply in the same way that we can routinely apply supervised learning. Okay, so there are many applications for this. I'll go through some of them in a moment. But that's the essence of what this is about. We can solve these one-step reinforcement learning problems routinely, systematically, all over the world. Okay, so why else are you interested in this? So I gave you two reasons earlier. One reason is you really want a system that gives you the right signal to get the right answer. And sometimes you just can't do that through editorial labels. The other reason was sometimes things are non-stationary. And you just need to have a system that can learn rather quickly in a non-stationary setting. There's another important reason here, which is typically paying somebody to label things is expensive. And so if you have free interaction data, then not taking advantage of it just seems kind of wrong. Right, so that's reason number 3. And there's a fourth reason, which is I guess it's not the one that you tell your manager, right? So what is AI, right? AI is kind of a buzzword. Everybody has their own interpretation of what AI is. This is how you know it's a buzzword. I remember when big data was a buzzword, and we had this editorial book. And so we invited a bunch of people to write about their big data algorithms. And I went through and I made a map of just how big the data was in each of the big data chapters in that book. And I think it varied over about 6 orders of magnitude. Right? So this is a supervised learning definition of AI. This is what people are commonly using to mean AI these days. And that's kind of reasonable in the sense that this is what image recognition is. It's a function programmed with data. But it's not very satisfying to me. I think AI should be an economically viable digital agent that explores, learns, and acts. And it feels more like, it's not like artificial general intelligence. It's not like you have a human there, but you have a system which is it's getting input, it's discovering something about that input, it's using that to act in the world, and then it's learning more from acting itself. And so this to me is where the fun is. So this is not the reason you tell your manager. This is the reason maybe why you actually do it. Okay, so there's these two different flavors. There's the multi-step reinforcement learning, where you have these special domains, typically simulated, where people have managed to solve games very well. This is backgammon, which was actually solved in the 1990s by Jerry Tesaro using reinforcement learning. This is Atari, and this is Go. These are the kind of the big ones that people have seen in the news and whatnot. If you think about what's going on here, it's easy to phrase the problem you want to solve. Did you win or lose the game? How many points did you get? You can define the reward that you want to optimize very well here. So you can optimize against the right signal. These solutions typically don't work at all if the game changes over time. They don't really cope with non-stationarity. Often finding that solution is very expensive because it takes multiple PhDs working on the problem for quite a while and with a high uncertainty to succeed. And in some sense, it is kind of getting at AI, because when people solved Go here, their solution came up with strategies which people had never thought of before. And that's pretty cool. At this point, I think it's, my understanding is that the solution is so good that there's no real hope that a human will actually manage to compete directly with a computer and Go in the future. Okay, so with contextual bandits, you're solving immediate reward reinforcement learning, which is a more limited problem. But, okay, what does that mean? So sometimes the immediate reward that you're solving is not the right signal. Sometimes it is. So it's the right-ish signal. Often you need to think about what that immediate reward signal you want to optimize should be. You can actually cope with non-stationarity in the problem pretty well. This is not formalized in the theory very well, but in practice, we end up dealing with non-stationarity all the time, and it works. And then, of course, you save money, or maybe even you make money, and there's some sense in which this is getting at AI, because it's an economically viable digital agent. All right, so another example where people have tried these techniques is in wellness. So maybe you want to observe features of a user and a choice of advice. So for example, if you want to encourage somebody to exercise during the day, you can say, hey, exercising is a great thing to do. Or you can say, your friend over there did more exercise than you. Which of those is the right thing to do? Well, maybe it depends upon the person or the context in various ways. Now you can try to choose this advice so as to observe how many steps are walked or how much exercise they did, trying to promote healthy behaviors. This is another common application area for these kinds of techniques. Okay, so then you can look at where real-world applications of reinforcement learning are actually happening. We did news article recommendation back when I was at Yahoo in 2010. It's been used for ad choice and ad format and education. This is like, this is online education. So you would say online learning, except that would be very confusing. So you're on the computer working with a program. That program is adjusting what it's doing based upon what you're doing with it. And there's a learning process going on underneath. Music recommendation, robotics. You wouldn't think that you could apply this kind of thing in robotics, but it turns out that if you do the right kind of, if you define the immediate reward in the right way, this is actually very compatible with robotics, because in robotics you want solutions which don't require very many samples. Doing things with a real robot takes a lot of effort. And so solutions which don't require 1 million samples, which require only 100 or 1,000 samples, are much more reasonable. And then that encourages you to spend some time thinking about how to choose your reward function so that you can just optimize the immediate reward, and then something good happens. And then, of course, the wellness health area, there's quite a bit of work over time. Okay, so so when is a problem solved? Right, so we talked about when a problem is solved for supervised learning. For reinforcement learning approaches, you think of a problem is solved if an outcome value can be measured, and many times. So for full multi-step reinforcement learning, I think that's really a work in progress, because there are these trivial counterexamples which can break our common algorithms. But for immediate reward, contextual bandit style learning, this is where we're at. We can solve this just as effectively as for supervised learning. Are there any questions? Okay, so the claim is that this is actually a good fit for many real-world problems. That it's a better fit than supervised learning, for example, for many of these problems. And now, what we're going to talk about next is what we can do. So how do we craft algorithms in this for contextual bandit learning, and what can we prove about these algorithms and so forth. So I want to lay out the foundations. So in particular, how do you know if you have a good contextual bandit learning algorithm? How do you actually do the learning, and how do you explore? Okay, so we're in a setting where we observe X, we have a policy which chooses an action, and then we see the reward. Now I've just attached X will be the observation, A will be the action, and R will be the reward. Okay, and our goal is just to maximize the sum of rewards over time. So this process repeats over and over again. We're thinking of the world as stateless, so the action that we take now doesn't affect the reward that we'll observe later. Stating this in terms of news article recommendation, the news article that I recommend to you doesn't affect the news article, your response to the news article that I recommend to you, right? Okay. So I'm going to think about policies. Policies are maps from features to actions. They're functions. So this would be a neural network policy. This would be a decision tree style policy. In each case, a policy is just some way of mapping from our context, X, to the action that we're going to take. So this is the same, viewed as a function, it's the same object as a classifier in supervised learning. But the key difference is that a policy acts. So a policy does something in the world. And that's actually really important to the process of learning, because the way that it acts is going to influence the reward that it observes, which is going to influence the training that it happens to get the next function. Okay, so the key distinction there is just a policy is something that acts. Okay, so a fundamental claim is that you need to do exploration in this setting to succeed in general. So if you think back to the, do you know if I'm interested in an article about Ukraine, you can't know that if your policy never has any chance of exploring that choice. So maybe you have a policy which says that a person is interested in a space article. But, okay, so if you explore a little bit, sometimes you display a food article, then maybe you discover they're actually more interested in a food article. So that process of gathering information requires some form of exploration. And okay, so there's actually several kinds of exploration which can occur. The best one turns out to be random exploration. So if you're going to be exploring randomly, it will turn out that we can do a bunch of good things with the data. We can evaluate how a policy performs offline using that random exploration data. Okay, so if we are exploring, let me go back. I want to emphasize one thing. When you say randomization, often people think uniform random, but turns out that the best kinds of exploration are not uniform random. The best kinds of exploration are much more intelligent than that. We'll discuss that in more detail later. Okay, so if we are exploring, then we have these quads of information. We have the features, the observation X. we have the action that we took, we have the probability that we took that action, and then we have the reward that we observed after taking that action. So we have this XAPR quad. And then, okay, so we have this experience. We have a policy, pi, which maps the features to the action. And the question is, how good is the policy pi? So the traditional solution to this is to deploy pi in an A/B test, right? Wait a couple weeks and see how it performs. It turns out that you can do it a different way. So in particular, you can use this historic data to value the policy. So we're going to value the policy by saying we're going to take an empirical average over the events. Okay, a high reward is good. If the policy agrees with a randomly chosen action, then that's good. This is an indicator function, which is 1 when there's an agreement and 0 otherwise. And then we're going to divide by the probability of the event. Okay, so that last bit is a bit unintuitive, right? So this is intuitive. This is reasonably intuitive. The division by p is less intuitive. So this is called maybe a propensity score or probability of an event. It's fundamentally the probability with which that action was taken. Okay, so a claim is that for every policy and for any distribution generating the features x and the hidden reward vector r, the expected reward of the policy's chosen action is equal to the expectation of this estimator. Okay, so this is a very strong theorem statement because this is equality and it's for all. Right? So that's what we want in terms of a basic fundamental thing. And now, why is this true? So it turns out this is actually trivial to prove. You say, okay, so this holds for every distribution over x and r vector, but I'm just going to pick a single x and r vector. And then I'm going to prove it for that. So it'll then apply to every distribution. So if you pick the x and the r vector, the only randomization left is over the action. Right? So you're taking, I'm taking the expectation inside of here, so there's just a single event left. All you have left is the random action. I've decorated the reward with the action associated with it and the probability with the action associated with it. Okay, so expectation is equal to the sum over the actions, the probability of the action times the thing inside. And then the probability of the action cancels with the probability of the action. So this is where the magic happens. This is why you have the probability of the action. And then the indicator function is going to cancel with the sum. You'll just end up with a reward of the policy's chosen action. So this is the simple proof, which says that you can achieve this kind of statement. You can prove that you can value a policy using this offline data. Right? And that means that instead of taking 2 weeks to evaluate a policy, we can take a minute or less. Depends on how much you want to parallelize. And that's amazing because that puts us into the kind of setting where supervised learning is. In supervised learning, you can have a test set. Here, we can have a test set. Right? And that means we can iterate much faster on trying to figure out what the right features are, what the right representation is, and we can just learn. Okay, so this is from real data. We're doing a news article recommendation on a startup called Complex. The black line is the actual observed performance of the system. This teal line that's just behind the black line is the IPS estimate of the black line. You can see that it's close up to statistical error. And then this lower teal line is the offline estimate of another policy. In particular, this is the editorial policy. So in some sense, we're comparing with supervised learning. There's editors at this startup who are choosing which news articles to display. And in fact, we are doing better. Right, so we did something useful. Okay, so what's not easy to visualize is the fact that, okay, this could be an A/B test. We could be just doing an A/B test between the editorial policy and our policy, and you could draw the same graph. The key difference that this provides is that you could have 1,000 lines on this graph, which you wouldn't actually do on a graph, but you might want to do 1,000 different evaluations or effectively 100 million even in the process of trying to figure out what a good policy is. And that's because you can reuse the data points. If you think back to what's going on here, see, the key observation is that it's the action which is mediating which reward you observe, not the choice of policy. And that means that every policy which is choosing that action is being explored when you choose that action. Right? So you can have, maybe we have 10 different news articles we could choose amongst. Maybe we have 2 to the 300,000 different policies. If you think about the bit representation of a complex function, 300,000 bits is actually not very large. So the number of policies is very large, but the number of actions is relatively small. Every policy choosing that action is explored when that action is explored. There's a sharing of information, which is the key advantage that you get over A/B testing. And we're not discussing here the confidence intervals. You do have to worry about them. But in general, the confidence intervals are going to have a central limit theorem type property. So the number, if you want to evaluate 1 billion policies, you need the data for 21 A/B tests because you're using that exponential tail in the central limit theorem to win. Okay, so I showed IPS is the simplest approach. There are better ones. These are useful. They give you faster convergence. But the kinds of theorems that you're going to prove with these are of the same flavor as what I just showed you. Okay, so that's evaluation. Once you can actually evaluate policies, if you can evaluate many, you actually already have a learning algorithm. You could just guess a policy, evaluate it, and then if you don't like the result, guess again, evaluate it, and keep going, right? But you would like to be able to learn more efficiently than that. Certainly, most of our learning algorithms operate in a better fashion than this. So how do we learn to maximize expected reward of the policy chosen action? So it turns out that you can actually take any supervised learning algorithm and use it to optimize for the reward of the policy chosen action. There's generic techniques for doing this. I call them reductions. So an obvious approach to optimizing this is to use the theorem that we just proved. We can instead optimize this, right? So the value according to our estimator of the policy. So if we rewrite it, the reward is equal to R over P if the policy's chosen action is equal to the random action and 0 otherwise. Now, if you think about it, this is very close to multi-class classification. Because in multi-class classification, you have one right answer and a whole bunch of wrong answers, right? The difference is that this is not equal to 1. If this was 1 here, So if we have a reward of 1 for one action and a reward of 0 for other actions, it would be just plain old multi-class classification, and we could just apply our multi-class classifiers. Okay, so but there's a trick. We can take, we can say this is a 1. We're going to define an altered reward where the good action has value 1, but we're going to say that there's an importance weight of R over P for that sample. So importance weights are a common trick when you're playing around with learning algorithms. What you're doing is you're saying that this sample is R over P more important than a typical example. Right? And then the expectations end up working out right, and you're optimizing for the same, the optimal policy for this reward structure is the same as the optimal policy for this reward structure. Okay, so that's good. So we can do importance weighted multi-class classification. So there are some classifiers which don't take importance weights in, but you can just sample from the importance weights according to their value in order to apply it to any multi-class classifier. Just a moment. Okay, so this is saying something very basic. This is saying that all of the learning algorithms that we have from supervised learning can apply to contextual bandit learning. That's a really powerful fact. It means that we can go and apply a decision tree, neural network, whatever we want, and use whatever our favorite tools are to solve these problems. So that's great. Vopal Wabbit is a machine learning toolkit that I also started about 11 years ago, which focuses on online learning. And in particular, it has these algorithms built in. So there's a reduction associated with this. I would call this the IPS reduction. And it is implemented inside of VW. So VW, it's been 11 years. It has a BSD license. It has a mailing list. It's on GitHub. Lots of people are using it. Lots of people are contributing to it. It has a command line interface or C++ or many different languages. And it gets used by many different companies. So if you want to go and experiment with these algorithms, you can do that very easily with VW. So I'll show you a little bit about this. If you're trying to do contextual bandit learning, you have a set of features, and in VW you can just feed in raw words and we'll use hashing tricks to turn that into features. And then you have this special label format. So there's the action. VW uses a loss rather than a reward. So you're saying you have a loss of 2 associated with action 1, which was taken with probability 0.5. And then you can just shove in the data set with the appropriate flags. You can use either, so there's DISH CB, which is just contextual bandit learning where you have one example per line, where this is the label format and this is the feature format. Or you can use CB_ADF, which says that you have action-dependent features. So often in these settings, you want to kind of be able to express a set of different features for each individual action. And there's a way to do that as well. So you can train on a pretty large data set. This is a supervised data set where I randomly took different actions and asked what the loss was for that chosen action, right? This is the Reuters document classification data set. You can say, oh, I want to use n-grams and skips, and I want to use 24 bits for my hash function. And you can end up getting about a 4.8% error rate, which is pretty good on this data set. So if you're trying to do supervised learning, so supervised learning always has more information available because you know the loss of all the different actions. If you try to do supervised learning, you get down to about 4.5%, I think, on this data set. So even though with contextual bandit learning you have less information, you can still manage to get very close to what you would get if you knew the loss of every single action for each event. This training, by the way, takes about 10 seconds for 760,000 examples. Okay, so I showed you the simplest way to transform contextual bandit data into supervised learning data, right? There are many other algorithms for trying to learn from this sort of data. There's policy gradient, which you see fairly often for the multi-step reinforcement learning. There's several different families of reduction approaches, which are typically more effective than the IPS approach. In particular, I think this is my favorite one at the moment. So here what happens is you regress to predict the reward given the features in the action, with a caveat that you use the importance weights in the right way to make this be an unbiased regression process. Okay, let's segue for a minute. We can evaluate a policy in a contextual bandit setting. We can learn using any supervised learning algorithm. There's a key difference, though, between supervised learning and trying to do reinforcement learning in the real world, which is that in the real world, typically the reinforcement learning is happening in an online setting, right? And typically when you're doing supervised learning, you're doing it in a batch offline setting. So in a batch offline setting, people are used to having a training set and a test set. And then maybe you have a holdout set so that you don't contaminate things, so that you get fair evaluations. That doesn't work very well in an online setting because it's not the right structure. Instead, what you want to do is think about how you can evaluate an online learning algorithm generically. This is actually approximately the first paper that I wrote. Not quite, but very close. So you can use progressive validation to solve this problem. So the way progressive validation works is you see a unlabeled example, and you make a prediction, and then you see the truth. And then you see an unlabeled example, you make a prediction, and you can compute a loss. So you're always predicting one ahead of where you're seeing an example, right? And so that process continues. And now you have a loss for each of these individual examples on the prediction that you made before you saw the label. And now you can take the average of those losses, and then you can prove various things about this. You can prove that the average loss across each of these examples is an unbiased estimate of, okay, so it's a little bit hard to explain. When you're doing online learning, you're changing your policy at every individual step, right? So there's no one policy. You have a policy which is changing at each step. Every individual policy in that sequence has its own value. You can ask, what is the average value over that sequence? And the claim is that the progressive validation value is equal to that, is an unbiased estimate of that average value. So another way to say this is progressive validation is estimating the value of the policy which randomly chooses one of these policies in the sequence. Okay, so that's good. It's unbiased. You can also prove that the deviations in this are like a test set. So that's really good. That means you can trust it like a test set. And then you can start doing the kinds of things you're used to doing with test sets in supervised learning. Okay, so that's a minor thing. That tells you how we can try to do evaluation in an online setting, which is what we typically need to deal with when we're trying to do these reinforcement learning tasks. Okay, so now how do you do exploration? The simplest algorithm is epsilon greedy. When you do epsilon greedy, what happens is with probability epsilon, you act uniformly at random. With probability 1 minus epsilon, you act greedily according to your best learned policy so far. This is kind of the baseline algorithm. You always want to do better than this. So there are better algorithms and the better algorithms have a particular flavor. They maintain some ensemble and explore amongst the actions of this ensemble. And exactly how they maintain the ensemble varies quite a bit. However, just recently, we did a evaluation on 500 different data sets of what is a good exploration algorithm. So I'm going to show you what these say. So how did this work? Well, we got 500 supervised data sets. Anytime you have a supervised data set, you can pretend that it's a contextual bandit data set by just probing for the loss of individual actions on each example. Okay, so this is at the archive there. There were many different approaches that we evaluated. The two exploration algorithms which gave the best performance were this regressor confidence intervals and this cover approach. And here you can see a scatter plot where we're looking at the loss of the cover approach and the loss of the regressor confidence bound approach across different data sets. And you can see that there's no real dominant structure between the two. Okay, so, yeah?
Just a quick question. How did you handle stationarity with these supervised learning data sets?
Yeah, so we permuted all the data sets before we did anything. So the problem that we were solving was inherently stationary. So that's a caveat here. It may be the case that in non-stationary settings you need to have more exploration than is indicated by these experiments. Okay, so a surprising thing that we discovered was that if you completely ignored the need to explore, then on these data sets, greedy actually worked pretty well. So greedy was also amongst the top three. And it depended upon the data set whether or not exploration was truly required in practice or not. And I guess our hypothesis about why this is has to do with this observation about non-stationarity. Okay, so let me try to explain the two exploration algorithms which showed the best performance empirically. And I'm just going to explain them at a very high level to get the gist across. And you can go read the individual paper for each of those to understand more detail. Okay, so the regressor confidence bound. Okay, so what happens here is we're going to, for every action given the features, we're going to predict we have a predicted value. Okay, so that's pretty straightforward. If you're just doing classification, you would just take the largest predicted value and you would go. But given the information that you have so far, you actually have a version space of possibilities because there's a lot of predicted values that you could converge to as you see more and more information. Right? So we want to think about this version space. So And the convergence for this version space may be non-uniform. So maybe we're very sure about this predicted value here. And maybe we're very sure about this one. This one, well, it could be a little bit higher, but it could be a much lower. This one, it could be a little lower, but it could be much higher. So the view to have here is that there's a set of all the possible regressors. And as you get more and more information, you're going to say, oh, this one cannot be the right answer because it's dominated by others. So you start throwing them away. And you start narrowing in on the set of, on what the best predictor of the reward is. So at any moment in time, you haven't fully narrowed in, but you've thrown away a lot of possibilities. So you've narrowed in, and now at this moment in time, what are the allowed set of possibilities according to this narrowed in set? Okay, so, and then how do you get at that efficiently is much more complex. But this is what's going on. You're thinking about that version space of allowed possibilities. Now, once you can compute this version space, you can say, what is the largest? And you can choose according to that. So if you're familiar with the Banach literature, this is similar to an upper confidence bound algorithm. And the trick here is, how do you work with an arbitrary version space of functions? All right, so then what is cover? So this is, again, we're going to be thinking about version spaces. We start with all two-layer neural networks, or all policies in our set of policies. And it's all depth 5 decision trees. As we see more data, we have a version space, which is the set of policies which are allowed by the representation and the data that we've observed so far. And now, this still may be an extremely large number of policies. So you would like to be able to represent this much more succinctly. So we're going to have a training process which maybe represents which has a policy which is kind of your best guess, but then it's going to also cover the space. We're going to try to learn a few more policies which are at the border of the set of allowed policies. So we're going to train policies to avoid the predictions of other policies, as well as optimize the performance, the reward that we observe. So we're going to train to get a cover on the version space. And that's, so we represent explicitly just a small number of policies which are covering the version space. And then we're going to act uniform randomly over these covering policies. So that's what the cover approach does. So I should say that the experiments that we did here were not the experiments where we just kind of like blindly applied things. For each approach, we try to come up with different kinds of tricks to make them work better. And I guess the one thing that surprised me is Thompson sampling approaches, if you're familiar with those. They're, since he's trying to sample uniformly from the version space, we could not make that work as well as this kind of approach. Okay, so where are we at? We can evaluate policies, we can learn, we can evaluate online, we can do exploration, and now the question is, can you evaluate exploration algorithms? Right, so that's even more tricky. And this is, I think, the place where it starts to become a delicate process. Everything else that I've told you so far, I think you can just do routinely, and it works. There's some caveats here and there, but you can get used to those caveats, and it will work well. Here, it starts to become a little bit tricky. and I'll explain why. So we can think back to doing the evaluation of an online learning algorithm. You see an individual data point, and then you can check to see if the policy that so an exploration algorithm in general is going to be adapting over time. And the way that it adapts is dependent upon the data that you feed into it. So the question is, which data are you going to feed into it, right? If you feed all data into it, then you get data. So I'm not starting well. Suppose we just have XAPR. We have these quads. We have a whole bunch of collected data in the past. We would like to evaluate an exploration algorithm. The exploration algorithm, however, is dependent upon what it learns from. So you want to feed data into that exploration algorithm, which is representative of the data that it will get in the wild if you actually deploy it, not the data that you gathered, not the source that you actually gather data from. So you see an event, and now maybe that in that event, the action taken agrees with what your what your exploration algorithm said to do. Okay, so then you keep it. You feed that into the exploration algorithm, it updates, and now you see another event, and maybe it does not agree, and so you throw it away. And you see another event and doesn't agree, you throw it away. You see another event, you throw it away. That one you keep. You just keep going forward, keeping the events that agree with the randomly chosen action in the past, and using those to update your exploration algorithm. Right, so you can run forward using this rejection sampling approach. Okay, and now, so what can you prove? Well, you can prove that the realized history is unbiased up to the length observed, which is a much weaker statement than we proved previously, because it isn't saying anything about the deviations. And it's also, it's just talking about up to the length observed. So the length observed here is 1, 2, 3, 4, 5, 6. Not, it doesn't include all of the rejected samples. Are there questions about this? Yeah.
Actually, I have a very small question. I mean,
Yeah.
let's say that you want to evaluate an exploration algorithm that always takes the same action.
Always what?
Takes the same action, so it doesn't
Yeah.
explore. Okay, just for sake of understanding. And you evaluate on the history where the algorithm that you used was always picking the best action at each stage. Then your naive, stupid algorithm is going to be evaluated on only the good example.
Yeah.
So it will have a very good performance, a very good offline performance, but a very bad online performance. Is that correct? Or?
Yeah. So if you're trying to evaluate an exploration algorithm, which always uses the same action, then you don't actually need to use this approach at all. You can go back to the previous approach that I showed. Let's go back here. Right, this one. And in particular, you can do the IPS estimate for each individual event. And we know that's unbiased, so you'll just be able to get an unbiased estimate of things. Right? And that's going to be the most data vision thing. So what you're taking advantage of here is the fact that your policy is not changing. So if your policy is not changing, then none of the complexity for the last bit is going to come into play. Yeah?
Just to follow up on that.
Yeah.
So the exploration evaluation, the way you're evaluating the exploration is that you've shown here is for deterministic exploration policies, or can it also be generalized to?
It's easy to
ones?
generalize to stochastic exploration policies.
Okay.
Basically, the indicator function becomes a probability according to the policy you're trying to evaluate.
Okay. All right. Thanks.
Okay, so the weakness here, okay, the strength is that this is actually an unbiased estimate of what happens. The weakness is that it's like one Monte Carlo estimate of what happens. So it's not saying anything about what would have happened in a different realization. So in particular, you could have an algorithm which says that if I take 3 actions in a row that are the same, then I'm going to segfault. And maybe that's not realized by this particular sequence of events, right? That seems essential to the nature of the problem you're trying to solve, and so it's hard to get rid of that. The other thing which I think you come up with in practice is if the world is non-stationary, the fact that we're only accepting a subset of the events is kind of problematic, because it means that in the simulation, time is advancing faster than in the real world. So you may get better performance in the real world than you get in the simulation. All right, so I'm about done. Just a couple more things. So contextual bandits are a good fit for many real-world problems, and they're fundamental questions that have good answers. Right, and so that's kind of the key thing. And then the last bit is there's a decision service that we've been working on, trying to make it to where anybody in the world can use these techniques easily. So it's not quite enough to have an algorithm. You actually need a platform which can reliably make predictions and do the learning and so forth, which is what this decision service is in fact doing. So right now you can use this for kind of web page recommendation like tasks pretty easily, but in the future it's going to be a lot more than that. So the idea here is that you want to kind of eliminate bugs by design in the infrastructure, in the way you design things. So there's a system which logs the features, the action, the probability of the action, and the key at the moment of that you make a decision. And then later on, that gets joined with a reward and the key for the event after some pre-specified time. So I feel like I'm switching gears too fast. When you go and you try to apply these things in practice, what you often discover is that the problem is not the algorithm. The problem is, in fact, the way that the information is plumbed in your system. I've run into many bugs where, for example, maybe instead of logging the features, they logged a reference into a database, and then the database changed, and so you could never recover the features again. Or maybe the key for the event is just not the same as the key for the reward, and so there's no way to join the reward to the event effectively, and then you lose, right? These kinds of problems are what really trips you up when you try to apply these algorithms in practice. So this is a system which tries to get this right systematically and generically so that it just works. Right, so there's a guarantee in the system that the features used during exploration and learning are the same. So you don't suffer from a mismatch between the learning process and the exploration process. You avoid many other of the issues that I just showed you. All right, so of the publicly available services of this flavor that people can generically use, there's the decision service, which has the offline evaluation and optimization. And then there's a few other systems which people have been putting out, which do some things along these lines. So this is kind of a new category of services which I think is arising. And I expect that this will become much more common over the next 5 years. All right, so that's it. This is Goldilocks. I mean Goldilocks in the sense that so Goldilocks, I think, drank the soup that was just right. And so there's kind of supervised learning, there's multi-step reinforcement learning, and in between there's contextual bandit learning. And right now, I think is a Goldilocks moment for contextual bandit learning. Thank you.
So we do have time for a question.
I would like to ask you the following. Once we have finished with our evaluation process, either online or offline, something that I have been exposed to in practice is to debug essentially the whole pipeline, analytical pipeline I have constructed so far, which includes not only the last steps of model building, tuning, and evaluation, but also what we used to call it pre-processing steps on cleaning the data, on extracting the features, selecting the features, etc., etc. So something which is very, let's say, practical in industrial setting at least, is how we can use, let's say, evaluation of pipelines which are put in production, okay, to debug actually the design of the pipelines that we have used it, and of course to what extent this new metaphor for learning, okay, could help us in that respect.
Yeah. So I don't know if this metaphor for learning is particularly helpful, but what I can tell you is that if you design the system correctly, which we're trying to do, then you can have the online process be completely reproducible offline. Right? And so how do you do that? Well, there's a bunch of tricks, but you use pseudorandom numbers. You log the key of the model which is doing the exploration with the event that it created. And then you checkpoint those models offline. And then your learning process itself becomes, the learning process itself is a deterministic function of the pseudorandom numbers that you feed into it. And so you can get the entire, you can reproduce the online system offline, which can allow you to debug. So I found this to be super essential because if you have an evolving process that is doing something strange and you can't reproduce it, I think you just can't debug it, basically. And I guess there's been about 2 times in my life when that happened, and the ability to debug this was very, very helpful. So I think the short answer here is that, in general, this paradigm is more difficult to debug. But you can make it be only as difficult to debug as supervised learning by making the online process reproducible offline.
Another question? Yeah.
So thank you for the nice presentation. So you showed a lot of methods that are based on plain, like importance sampling, which is a basic way of doing sampling. So do you think you can gain something by doing like raw block realization or MCMC that are more sophisticated?
So I didn't really delve into the more sophisticated approaches, yes. But for almost everything that I talked about, there are more sophisticated approaches and they are useful. They're not like amazingly useful better, but certainly you should be using them in practice because they're just better than the ones I showed you. The ones I showed you are just the basic gist of what's possible, and then there's embellishments, and the embellishments are useful.
So we have time for last question, maybe? Yep.
Thank you for good presentation. And my question about IPS metric, how to use this for deterministic strategy.
Yeah, so one thing that I didn't mention is, oops, what happened? I think I went too far. Let's see if I can, oh no. All right, so one thing I didn't mention about the evaluation is that the regression-based confidence bounds is a deterministic exploration strategy, which is, I mean, it's a problem if you want to do offline exploration. So there's two things to say there. One of them is, I was happy that at least one of the randomized exploration strategies is actually competitive. That's the cover approach. So use the other approach, which that makes it easy. The other thing that you can say is that if there's exploration going on, which doesn't have a recorded probability associated with it, there's okay, so how do we think about what the exploration is? So, let's go slightly forward to here. So you have a policy which over different time steps is changing. That policy is given by this complex process of creating a version space and whatnot. At different time steps, different actions would be chosen. And so you can ask, if you chose it at a random time, if you picked a random time step and then did the evaluation at that time step, what would the probability of the action be over the random choice of time step? Right? Okay, so in general, it's computationally intractable to keep track of this because you'd have to kind of evaluate, you have to checkpoint your learning policy after every update. But nevertheless, you can either approximate this or you can try to estimate it using supervised learning techniques, which allows you to recover a probability for the action when you have this kind of deterministic but evolving policy. And that allows you to reconstruct a P, which then would allow you to do offline evaluation.
So answer is estimate P from.
I mean, in theory at least, it's not even estimation. You can just calculate it because you could checkpoint the policy at every time step, and you could evaluate every policy you checkpointed on an individual event to figure out the probability of the action over the different time steps. But in practice, I think estimation is what you end up doing because it's a very computationally heavy process.
Okay, thanks.
Okay, then I think we should thank John again.
Thank you.